let's imagine that we have an electron in the hydrogen atom, and its wave function is psi of r theta phi, so it's the solution to the time-independent wave function, or at t equals 0, we have something like this. So r21, that's a radial function. We have a y10 plus root 2 over 3 r21 y11. So the quantum numbers are n is equal to 2, then we have L is equal to 1, and M is equal to 0 or 1. So let's consider measuring L squared, right? So we want to measure the L squared value, and right, so L squared psi, we know that gives us, if we are in an eigenfunction of L squared, which we are, then that applies, and therefore, because L is equal to 1, it's 1 times 2 h bar squared. So we have 2 h bar squared. That's the value that you can get, and the probability is 100% because the L quantum number is unique. So let's say we want to measure Lz. What's the value of Lz? Right, so in an eigenstate of that, we have m h bar psi. But in this case, we have m equals 0 and m equals 1 in this combination. And so we could get m equals 0, and therefore Lz is equal to 0, with a probability of 1/3. So the probability of that would be 1/3, and m equals 1, and therefore Lz equals h bar, with a probability of 2/3 in this case. What about the energy? Well, we only have one quantum number, so we are in an eigenfunction of energy, and so E2 with 100% probability. And notice that there is no time dependence to the probability. Psi of, let's say, r theta phi t modulo squared, not equal to, let's say, a function of time. Yeah, so we could write this as this function. So this quantity r theta phi t is equal to 1 over root 3 r21 y10 plus root 2/3 r21 y11 times e to the minus I, the value E2, t over h bar.